Hello again everyone, welcome back to ptet.chemistry channel. So my name is Dr. On, and in this tutorial video we'll go through this November 2015 paper 22. So this is a paper 2 variant 2 for the Cambridge International A-level exam, which is suitable for any 16 to 18 years old students all around the world. In this first question, we gotta fill in the gap. So we are given quite a few rows in the table here, and each of them represent a particle which could be atom. Some of them are atoms, such as the zero charge atom. Some of them are going to be anions, and the reason why I don't put ion here is because there is a term called cation here, and when they use cations is to represent positive ions. So when I have negatively charged ions, I am going to use the term anions instead of a general term called ions. So looking at electronic configuration, we should be able to tell how many electrons we have, such as these 1s2, 2s2, 2p2. So that is 2 electrons in the 1s, plus 2 electrons in the 2s, plus 2 electrons in the 2p. There are 6 electrons total. And we need to know how many protons there are, and we can get that from the identity of the element. So carbon 13 is going to be carbon, and carbon has 6 protons in the nucleus according to the periodic table. Is element number 6, and carbon 13 simply means the mass number or the nucleon number, which is not the same as relative atomic mass, because relative atomic mass is the one stated in your periodic table. It says that this is relative atomic mass, and you know from AS chemistry, the definition of relative atomic mass is clearly something which is not the same as the definition for mass number or nucleon number. So they are not the same definition because they are not the same thing. So just be very careful there. So what do we have? We have 6 protons, so that's the number of proton, or what you will call atomic number. And if that is true, 6 electrons and 6 protons, that means we have 0 charge, because the number of protons equal to number of electrons when you have atom. So which means this must be atom. And I can go straight to sulfur 34. Sulfur 34 is going to be sulfur, which is element number 16 in the periodic table. And I have 34 nucleons. The mass number is 34. And since I'm an atom, so that means I must also have 16 electrons. So I'm just looking at the periodic table, and I'm just looking at sulfur. How do you go from hydrogen to sulfur? So 1s2, hydrogen and helium, then 2s2, lithium and beryllium, 2p6, boron all the way to neon, and then you go 3s2, that is sodium and magnesium, and then sulfur is the 4th element, sulfur, 4th element in the P block. So you know it's 3p4 because it starts from aluminium, and then silicon, and then phosphorus, and then sulfur. So 3p4, 2 plus 4, 6 electrons in the outer shell, group 16 in your periodic table. Going back to the symbol for carbon 13, so you know these are the international standards, meaning to say we are doing the nuclide notation. So we are writing down the numbers to the far left. So 13 nucleons and 6 protons for the atom. Then sulfur 34 is 34 nucleons and 16 protons there. Now the next one is the second row represent a chloride ion with a -1 charge. That means the atom has gained 1 electron. We know that we know that chlorine has 17 protons, but now you gain 1 electron because you have a -1 charge. So altogether you are going to have 18 electrons. And when you have 18 electrons, we are talking about a fully filled outer shell. So it's gonna look like argon. So 1s2, 2s2, 2p6, 3s2, not 3p5 but 3p6, because this is an ion of a -1 charge. The name itself comes just from the mass number, because this is going to be chlorine 37, since the mass number of the nuclear number is 37 there. And just because you gain 1 electron, it's not going to change your mass that much, since the mass of an electron is only about 1/2000. 2000 times lighter essentially than the mass of a proton or a neutron, which are the nucleons. They are the particles inside the nucleus of an atom. Okay. Now to iron 54, what you could do is you know that this is cation, so that means you cannot total up the number of electrons and get the number of protons. And besides, there's an easier way to get the number of protons. If you just look in the data booklet in your periodic table, the atomic number for iron is 26. So we know that the atomic number, the proton number, or the atomic number is 26 for iron. And then this is iron 54, so we are not doing relative atomic mass from the periodic table. So your relative atomic mass show 55.8. We cannot show 55.8, we show 54 because in the nuclear notation is for a specific isotope. This is isotope iron 54. Iron, the mass number is the atomic number is 26, so there's Fe, and we have to consider that there's a charge, so there's 26 protons, and then I have 2 plus 2 plus 6 plus 2 plus 6 plus 6, as these are the number of electrons in each of these orbital. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 6 is 24 electrons. So I have 2 extra protons than electrons. I will have a net positive charge. I will have 2 extra positive charge. Therefore, I have a 2 plus charge there, this being a plus 2 cation. And like that, you get the easy 5 marks. Of course, you will do much faster in the exam where you don't have to explain to someone else and you're working with your own speed. But you got to be aware of the things that are confusing so that you don't make any mistakes in these kind of questions that are giveaway. In this second question, so we have the nature of bonding. We're talking about 2 spectrum of bonding. So what is meant by electronegativity? As stated in the syllabus, it is the power or it is the ability. We're talking about power or ability of an atom. We are not talking about molecule. We are not talking about ion. We're talking about an atom according to the specific definition. You can also see in the syllabus, of course, yeah. And this is to attract bonding electrons towards itself. So you're trying to attract bonding electrons towards itself. So when you are in a covalent bond, one atom which is more electronegative than the other will win the tug of war. The electrons will be closer to it and you will get a delta minus due to the electrons being closer to you. Now name and describe the type of bonding when you have equal electronegativity, things like chlorine and chlorine. There will be no winner in this tug of war because both of them are electronegative, but both of them have the same electronegativity, so they pull equally towards themselves, and as such there's no winner in this tug of war, and therefore the electrons lie exactly in between each of these, and therefore the bond itself is non-polar. And the whole molecule only contains one bond, and if the bond is non-polar, as a result, the whole molecule which comes from the polarity of this bond is going to be non-polar as well. This is element, and we know that it's non-polar, so you only have London dispersion force, or what you can call van der Waals forces, which is the same as London dispersion forces there. So what is the type of bonding when you have equal electronegativity? That's going to be called covalent bonding. Now they want you to describe the type of bonding. So they want you to describe covalent bonding. If you see in the syllabus, we do not describe covalent bonding as sharing of electron. That is the process. But then what we're talking about is what is covalent bonding. As with any type of bonding, we are talking about electrostatic force of attraction. But what is attracted to what? Electrostatic means something positive attracts something negative. In a covalent bond, you're talking about the shared pair of electrons, which is localized because it is kind of sandwiched in between the 2 atoms, the 2 nuclei specifically. So this is the localized shared pair of electrons, which are negatively charged, and they are sandwiched in between 2 positively charged nuclei. Positively charged nuclei, positively charged nuclei. Okay, that is the nature of the attraction, which is electrostatic, positive attract negative there. Now how about when you have very different electronegativity? So we have something that want to gain electrons, they pull electrons very close to one side, and then the other one want to lose electron. Now you can see a pattern here which resembles what you had learned from your O-level or GCSE or IGCSE chemistry. This type of bond is going to be called ionic bonding. That is because you have the metals which tend to like to lose electrons and give you cations, and the non-metals being the more electronegative atom would like to gain the electrons. So when we talk about ionic bond and we're asked to describe what is ionic bond, we don't talk about transfer of electrons. That is again the process. So as with any bonding, it is to do with the electrostatic force of attraction. But here, your lattice particles involve the oppositely charged ions, which are the cations and also the anion. So if you don't write oppositely charged ions, if you say between cations and also anions, it's perfectly all right. But if you write positive charge and negative charge, it's not okay, because when you have metallic bond, you also have something positive attract something negative. When you have covalent bond, you also have something negative attract something positive. So you have to specify what are the particles that are involved in forming the bonding there. Just to complete the story, of course, so metallic bonding has got nothing to do with these, because metallic bonding exists in metals, which are elements. So we're not necessarily forming any kind of bonding at all. But we do, because we have positively charged metal cations and we have the delocalized valence electron, that is for metals, whereas here you don't have the electrons, because all the electrons are localized. When you drew the dot and cross, the electrons are not floating around. They are inside the cations, they're inside the anions there. Okay. Question part C, we are given a bunch of molecules here as well as atoms. So this is F2. Argon exists as a single atom, as they are noble gases. They don't form any covalent bond at all. HCl is a gas until you dissolve in the water. Then it becomes a mixture, which is hydrochloric acid. So HCl is not hydrochloric acid when it is a gas, when it is pure. Methanol, CH3OH. Now explain why the boiling points of fluorine and argon are so similar. So when we talk about fluorine and argon, so both F2 and argon are simple molecular. In fact, all of them are simple molecular. Okay. Only need to break the weak London dispersion forces, or what we call van der Waals forces of attraction. So if you like, you can use London dispersion forces, and this van der Waals forces of attraction is between the molecule. And how do I know that? Because F2 is non-polar, since they have the atom of equal electronegativity. There is no permanent dipole, and of course this argon being a single atom is not going to be polar on its own. So these weak van der Waals forces of attraction between the molecules, this depends on, first of all, the total number of electrons in the molecule primarily. So this is the primary factor, total number of electrons, not valence electron, but total number of electrons in the molecule. Primarily means is the most important reason, but you can see that fluorine, actually I'm not going to talk about the secondary factor. Actually, this is the most important factor, the total number of electrons in the molecule. And both F2 and argon actually have same number of electrons, because if you look at fluorine in your periodic table, 9 and 19.0, so there are 9 protons in one fluorine atom. And when you have 2 fluorine atoms, how many electrons do you have altogether? You will have 18 protons, and you are a molecule with no charge, therefore you have 18 electrons. So you have 9 plus 9, which is 18 protons, but because molecule have no charge, therefore you will also have 18 electrons. Since the molecule has no charge, molecule is uncharged. And then you look at argon definitely has 18 electrons in the outer shell, fully filtered shell. You can do 282 configuration like what you did in secondary school, not 282, 288. Okay, 2 in the first shell, 8 in the second shell, 8 in the third shell. So 2 plus 8, 10, 10 plus 8 is 18, 18 electrons, 18 electrons. Same number of electrons, same total number of electrons in the molecule or the atom, similar strength of van der Waals forces. So I can say, therefore, similar strength of van der Waals forces that you need to break, and therefore, similar boiling point. Very, very similar there. Okay, oops. Now the next bit, why is the boiling point of hydrogen chloride so much higher than the boiling point of fluorine? When we look at hydrogen chloride, HCl, hydrogen has 1 protons. This is from hydrogen. And then you have 17 protons from chlorine, because chlorine is the 17th element. And then you get 18 protons. Surprise, surprise, because it's a molecule. So, that means there is no overall charge. Therefore, you must have 18 electrons in HCl as well. So having said that, 18 electrons in fluorine molecule, 18 electrons in HCl molecule, it can't be due to van der Waals forces. It has to be something else. So this one is actually a result of permanent dipole. As you could see, hydrogen and chlorine have different electronegativity. Chlorine have much higher electronegativity than hydrogen. So I can say chlorine is much more electronegative than hydrogen. And as a result of it, you are going to have a polar bond. So therefore, HCl bond and overall HCl molecule is going to be polar. But F2 is non-polar since the atoms have the same electronegativity. So what happened is we need to breaking permanent dipoles, and this is between the polar molecule. So between HCl molecules require more energy, and that is why you have a slightly higher boiling point, because you require more energy to break the stronger permanent dipole than breaking the weaker van der Waals forces or the weaker London dispersion forces. Something about comparisons of the energy required, energy expenditure, that should be alright. Last but not least, why is methanol having the highest boiling point out of all of them? You can see the trend now. Actually, I didn't have to calculate the number of electrons. I don't know why, but I should have read the question. Equal number of electrons there. But of course, it was quite fun to actually show you how they have equal number of electrons based on the number of protons, equal to the number of electrons, since these are all molecules. So methanol must have 18 electrons as well, but the boiling point is so much higher. So we talk about permanent dipole when we compare this polar molecule, and CH3OH must be polar as well. But between just the normal permanent dipole versus this, which must be a very, very, very strong permanent dipole, this must be the strongest intermolecular forces of all, because I know the question didn't ask for it here, but when the time comes, there might be a time when they will ask you to draw and show the hydrogen bond, between the molecule, or use a diagram to explain why the methanol has the highest boiling point like that. And of course, we label dipoles. We have to label delta plus and delta minus, and we have to have 2 different molecules. We're talking about boiling point, so both of them must be the same molecule. Between the molecule is intermolecular forces from the lone pair of the electronegative atom to the hydrogen bonded to very electronegative atom, fluorine, oxygen, nitrogen, the 3 most electronegative elements, conditions for forming hydrogen bond there. So methanol must have permanent dipole, but methanol must have a very strong form of permanent dipole. Methanol can form hydrogen bond between its molecules, but that is a statement that is not explaining yet. So can form hydrogen bond between its molecule. So we need to make a qualifying statement. So hydrogen bond is much stronger. Hydrogen bond is much stronger than just a normal permanent dipole. And also van der Waals forces. So we require a lot more energy to break. So therefore, H bond or hydrogen bond needs or requires a much larger amount of energy to break. Do you need to show the diagram here? No, you do not, because the question didn't ask. But I'm just saying that in certain years, in certain type of questions where they do ask you, show with a diagram, explain with a diagram why it will have a highest boiling point. Well, there you go. And you have to know how to do this in AS level, because it's an AS level question and they can ask you in A2 as well. That's the end of that 17 mark questions. Very good start to this paper so far. In this second question, explain the meaning of this term standard enthalpy change of reactions. So this is not your usual formation or combustion, that you usually get in AS, but there are 2 marks to it. One of the marks is definitely for these standard conditions, which are 29 at Kelvin and 1 atm pressure. Enthalpy change is just the enthalpy change. However, we know the enthalpy change is in kilojoule per mole. So it is not to do just with energy. It is per mole of something. Per mole of what? Just like for formation, we are talking about 1 mole of substance being formed. Just like for combustion, we're talking about 1 mole of substance being combusted. Just like for a reaction, what are we talking about? Per mole of what? Per mole of a stoichiometric. Stoichiometric. Gotta spell this properly. So stoichiometric means it's completely used up. So stoichiometric limiting reagent. Okay, because when you have 2 reactants, if they react in an exact ratio based on the balance equation, then obviously it's stoichiometric. But sometimes you have 1 limiting and 1 excess reactant, and it has to be per 1 mole of the stoichiometric reagent or reactant, because the limiting reactant completely used up. So your enthalpy change is a result of the limiting reactant being completely used up. That's why we have to talk about limiting, just in case we have a reaction where we have limiting and excess reactants, because we cannot expect every single reaction to be in a exact stoichiometric ratio there. So what can we say here? So it is the enthalpy change when what can I say, when reacting stoichiometric quantity. So there could be more than 1 definition for this, really. I'm just talking about per mole of what, right? When reacting stoichiometric quantity of limiting reactant or limiting reagent, the one that completely get used up under standard conditions. So these standard conditions will give you the remaining marks, because they did mention they want you to talk about standard stuff, right? So standard conditions, state it out. Some marking schemes, some textbook, they don't necessarily show you these. I always maintain a good habit of asking students to write it out, because the more you remember it, the better you will know it when the questions say what are the standard conditions. If you've never done it before, you'll be tempted to say, I don't know, I always write standard conditions, but you're expected to know it as they are part of the syllabus. Question part B is all about calculation. So this is about hydration. So in the new syllabus, hydration is now in the A2 syllabus. And this is part of the solubility of group 2 sulfate in A2 now. But regardless, the actual calorimetry type of question is still an AS question, so it doesn't matter, because they can still ask you anything that is related to the AS, even though it's an A2 concept, because they didn't ask you to define. They're asking you to do calculations based on the AS chemistry. So what we have is we have a polystyrene cup, and we support it on the beaker. We put a thermometer in there because we need to measure the initial and final temperature. We don't measure change in temperature because we cannot measure change in temperature. We can calculate change in temperature, which is the final temperature minus the initial temperature. So these are what you measure, this is what you calculate. Anyway, so what do we have? We have 45 gram of water, 45.00 gram of water. See how the accuracy is pretty high there. So this must be using quite a sophisticated mass balance that can measure up to 2 decimal place. But of course, we don't really measure the mass of water. What do we measure? We measure the volume of water, because the density of water is going to be 1 gram, 1.00 gram per cm cube, such that if you want 45.00 gram of water, you use a burette, which is very accurate. You use a burette, a very accurate apparatus, to measure this much volume of water. What else? We weigh in 3.01 gram of the solid, and then we get a temperature rising from 23.4 to 34.7. What is the amount of heat energy? So they want energy, and they want it in joule. So this is Q, which is heat energy, equal to mc delta T. Remember, the Q belongs to the water, because it's the heat energy transferred to the water, which means everything, mc delta T here, belongs to the water. Because C is the heat capacity, is the energy required to raise the temperature of 1 gram of water by 1 Kelvin. This delta T is change in temperature, when you have a change in temperature, whether you're talking about, let's say, 0 degrees Celsius to 25 degrees Celsius, then it's the same as talking about 273 Kelvin to 298 Kelvin. You will see that the change in temperature is the same because we are talking about change in temperature being a difference there. So it doesn't make a difference. You don't need to add 273 because this is change in temperature. If you are raising the temperature of water, how can the mass be of the solid? The heat capacity is for the water, the delta T is for the water, the M is for the water. So do not get confused. Number one mistake with students is they want to use the mass here. Then they will say, but I'm adding the mass to the water. Surely I should add the mass of water plus the mass of solid. Well, you know, the solid is reacting with the water, is getting hydrated, which means the temperature changes for the water. So, you know, it doesn't include the mass of the solid. So it has to be just the mass of the water. It's 45.00 multiplied by 4.18 multiplied by 3. Oops, see, I nearly make a mistake there. The change in temperature there. So we'll read the question again from 20. So it's going to be the final temperature, 34.7 minus 23.4. Change in temperature is the same. I do not need to add 273 there. So Q equal to, and just press your calculator carefully. Use bracket for the last computation there, so that you don't make any mistake. So 2125.53 joule. Do I want to run up? Perhaps not, because this is not the last bit of the question. But if you do decide to run up, I would say 4 significant figure will be okay. 1, 2, 3, and 4 for the mass given. 1, 2, 3 significant figure for the temperature there. 3 significant figure for the mass, which you haven't used in here. But usually, I mean, the next bit of the question is about enthalpy change and stuff, so you can run up in the last bit of the question. All right, I don't need to write down the unit because the unit there is already in joule, as there is joule per gram per Kelvin. Multiply by gram per gram cancel, multiply by the change in temperature. In Kelvin is the same as degrees Celsius for the change in temperature, so that cancel out. You get a unit there in joule there. The next one, calculate the mole of MgSO4 dissolved. So we need mass of Mr, so the mole equal to mass of Mr. So what is the Mr of MgSO4? Well, you look straight into your predict table. So Mg is 24.3 plus 16.0 times 4 for the 4 oxygen plus 32.1 for the sulfur, that is 120.4. So we had 3.01 gram of the MgSO4 divided by 120.4. So 3.01 divided by 120.4, I get 0.025 mole. So pretty straightforward there. But as for whether I want to leave it to 2 significant figure or not, perhaps not. These are 3 significant figure. This mass with 3 significant figure. This is 4 significant figure. My calculator does not decide on what is appropriate number of significant figure. I will reckon that I will add 1 more 0 at the end, such that I have 1, 2, and 3 significant figure. Calculate enthalpy change. You must include a sign. The moment you talk about enthalpy, we must already have a sign. We knew that the temperature rises. That was what we were told. The water is the surrounding. If the solution rises in temperature, that's because the reaction gives out heat energy. So 2125.53 is in joule. So I divided by 1000. So I multiply by 10 to the minus 3, which is the same as divided by 1000. I'll convert that to kilojoule. I divide by the mole of the solid that reacted, and I have a negative in front for my enthalpy change. And then I'm just going to cut and copy it onto here. So this was my heat energy transferred, converted to kilojoule by dividing by 1000, or multiply by 10 to the minus 3. At the bottom was my mole of the solid that dissolved. So previous answer, 2125.53 divided by 1000, or times 10 to the minus 3, divided by 0.0250. I get minus 85.0212. Too many significant figure. I would say 3 or 4 significant figure would be alright, because earlier you had the volume of the water used was 4 significant figure, but you also had these masses and the mole that we continued from these masses of the solid. They were all to 3 significant figure. Appropriate number of significant figure, 3 or 4 significant would be okay. 2 significant figure, not very okay. Sign, value, and unit there. Now in this next bit, use the equation below to construct a suitable, fully labeled energy cycle. What do we have? We have hydration, right? So it's Mg2 plus aqueous. Now this is a question which you might not get in the current syllabus because the hydration enthalpy, in terms of the definitions, you haven't really done it that much in your current syllabus until you get to A2. So what do we have here? So we are hydrating the solid. So that is the hydration of the entire solid. So this is what you want. And we have the enthalpy change of solution for the hydrated salt. So hydrated salt is on the right hand side. So this is enthalpy change hydration for the MgSO4.7H2O. This is equal to plus 9.60 kilojoule per mole. And we have the enthalpy of solution. So again, enthalpy of solution is now in the A2 syllabus. So this is probably more relevant to the A2 syllabus. But of course, if they ask you in practical, it's perfectly okay if they label the thing for you and then they ask you to work out what is this missing thing here. So Hess law says that the enthalpy change of a reaction does not depend on the path you take, whether it's direct route or indirect route. We're going to take an indirect route here. So this red color one, delta H equal to minus 85.0 kilojoule per mole, equal to the hydration of the MgSO4. Since we are in the same direction, I do not need to change the sign. I just keep it plus. But I'm going opposite direction, so I have to go this way. So I have to minus the hydration of that. So it's minus. Use a bracket. Always use a bracket. Direction matters. So if I want my hydration of the MgSO4, I keep this one here. I move the minus, this thing in bracket, minus and plus become minus. Minus 9.60 move to the other side become plus 9.60 minus 85.0. And your calculator should now show you minus 75.4 kilojoule per mole. Sign, value, and unit there. Okay. Actually, they are asking you for the calculation further down here for the last marks. They just want you to complete the cycle there. So I guess I can just move my stuff down there fairly easily since I'm working on screen. But yeah, that's why I thought they were a bit stingy when they gave only like 1 mark for this thing here. But anyway, so you do get another 1 mark for completing the calculation there, sign, value, and unit. So that's the end of that 7 mark enthalpy change question. In this question number 3, this is period 3 chemistry. So sodium, magnesium, aluminium, phosphorus, sulfur, and chlorine and argon. But when we talk about the oxide, the syllabus specifically stop at sulfur because chlorine can actually form quite a lot of oxides. We don't really deal with it in the we don't really deal with it in detail in the AS syllabus, but we do have some oxides of chemistry when they form ions, like the sodium chloride 1, sodium chloride 5 as well. Disproportionation case studies with the halogens. In this first question, give the formula of the oxide form when each element is heated in air. So we're going to have Na2O and MgO. As you know about this ionic oxide, we talk about the valency from your O-level or IGCSE days. So you know the valency follows the charge of the ions. And then you do the crisscross, and this will tell you how many of the ions you have. So you must have 2 of the Na plus and 1 of the O2 minus, such that you get Na2O. On the other hand, when you have MgO, Mg2 plus O2 minus, 2 and 2 for the valency, 2 and 2 for how many, but you need the simplest whole number ratio, so you only have 1 Mg2 plus and O2 minus. Al3 plus O2 minus, based on their valency, you get Al2O3. Now onto the phosphorus and sulfur. When you heat them in air, the sulfur is not going to go all the way to sulfur trioxide. You only go to SO2. Remember how difficult it is for you to actually go to SO3? You need contact process. You need equilibrium. You need conditions, certain conditions of temperature and pressure. Not going to happen when you just heat it in air. Alright? So that's why I start at SO2. As for the phosphorus one, depends on the oxygen. If you have not enough oxygen, it's going to go P4 or 6. But if you have enough oxygen, and they didn't mention in excess oxygen or not enough oxygen. So I'm going to say in excess oxygen, you can have P4 or 10. So both of them are entirely suitable and should be correct here, but not SO3 there, because to get SO3, you do really need some sort of equilibrium setting up in industry, unless you are in the upper atmosphere, and that is not true here. You're just heating up the element in air. In part 2, describe what you would see when sodium and sulfur are each heated separately in air, and give an equation for each reaction. Now the equation is probably the easier one to do first. So sodium plus oxygen, and you will get sodium oxide and H2O. We got to balance everything we write. So 2 sodium there means 2 sodium there, and 1 oxygen atom there means I have to balance this with 1 oxygen atom. But this is a molecule, so half times 2 give me 1 oxygen atom, and that equation is balanced. I don't need a stat symbol. The question didn't ask me for the stat symbol. Sulfur plus oxygen. Your first step in the contact process is to roast sulfur in oxygen to give you the sulfur dioxide, and then this sulfur dioxide can go to sulfur trioxide in an equilibrium step that you need to talk about Le Chatelier's and certain conditions to get a good yield of SO3. Now onto the observations. So what you would expect is as you form the Na plus cations, and we know about the flame color, the flame test is now in the AS syllabus. So back then it wasn't, but now in the AS syllabus, even the IGCSE, GCSE and O-level, you have the flame test of Ma plus, and that will give you the yellow flame. So we know that this will burn with a yellow flame. So you see a yellow flame as the sodium metal burns in oxygen, and you get the Na plus cations. Of course, then as you form this sodium oxide, instead of this metallic color of sodium, and then you will get a white solid forming. So you will get a white solid formed as a product. On the other hand, this sulfur there forms this simple covalent molecule. So obviously you don't have the flame test for cations because you don't have a cations. These are simple covalent molecule. But the sulfur actually burns in oxygen in a very characteristic color. So it burns with a blue color flame. So with a blue flame, this is a very, very special kind of color. If you had the opportunity to actually see this, you should try and see it, and you can check out YouTube for this color. Actually, it's actually pretty cool there. Okay. Down to the next question. The oxides show variations in their behavior. When you add them to water, it's either whether they're acidic oxide or basic oxide. So if they are acidic oxide, they're going to give you acidic solution. If they are basic oxide, if they dissolve in water, you're going to get alkaline solution or basic solution. So place the symbols of the elements. So the period 3 oxide, this symbol here. Sodium oxide and magnesium oxide are basic oxide. So that thing is going to be Na2O and also MgO. Al2O3 is amphoteric oxide. It is actually insoluble in water, but then it's amphoteric because it reacts with acids and also bases to give you salts and water. So acidic oxides are the non-metal oxides, the P4O6, P4O10, as well as SO2 there. Of course, SO3 is also acidic, but they were not from your list. They were not from your list in A part 1, so we cannot use SO3. But depending on which one you put in your list, whether you put P4O6 or P4O10, that depends on what you had written down here. State the bonding present. In this basic oxide, you have ionic bond. So they just want the bonding, they don't want the structure, not the structure. Be very careful. Bonding is not structure, structure is not bonding. And you have covalent bonding in the non-metal oxide there. Now onto the reactions of aluminium oxide. This is a key part of the definition. For this amphoteric oxide, you should at least know how to write them so that you'll be more prepared with them. Al2O3 plus HCl, I'm going to get AlCO3 as my salt, and I produce water. Our equation must be balanced, so 2 aluminium on the left, so 2 AlCO3, 6 chlorine on the right, so 6 HCl, 6 hydrogen on the left, so I need 3 H2O to give me 6 hydrogen, 3 oxygen there, 3 oxygen there. This equation is balanced. It is the sodium hydroxide one that is actually quite tricky to balance. There is more than one way of writing this equation, but the way I normally write it is in this format. You would expect to get aluminium hydroxide. This is a white precipitate that you get since your O-level, GCSE or IGCSE level practical. You get a white precipitate forming when you have sodium hydroxide in the presence of Al3 plus or Al3 plus in the presence of OH minus. This white precipitate dissolve in excess NaOH, and then it will dissolve in excess. That means you don't get this anymore. What you get in excess is this aluminium with 4 hydroxide. Al3 plus minus 1 times 4 is minus 4. Overall will be minus 1 charge. So what you get there is AlOH4 and then minus 1 charge there. Very important stuff there. This is your colorless solution that you get when this white precipitate that you form initially, hydroxide and Al3 plus, the white precipitate dissolve in excess sodium hydroxide or dissolve in excess hydroxide to give you a colorless solution there. So hopefully that makes sense to you. Perhaps I can just move this down somewhere so that we wouldn't lose that. Just give me a minute. Not really. No. Okay, I'll just write it down on the far left there. We got to balance our equations. You will see that I've written down as the plus and minus the ionic form so that we are not easily confused. But if you don't want that form, you can just remove the plus and the minus, and that will be entirely fine as well. So this is together as one compound. When we balance our equation, we'll have 2 aluminium on the left. So I will have 2 lots of this salt, the Na plus Al 4 times OH minus overall charge of the anion. Now I have 2 sodium. I have to put 2 NaOH. And now you will see that I have 4 hydrogen times 2, 8 hydrogen and 8 oxygen. Clearly, I don't have enough oxygen and I don't have enough hydrogen. I cannot be producing water there. Instead, for this particular equation, your water has to be on the left for you to balance this equation. So you have 2 hydrogen, you need 8 hydrogen. So you have another 6 more hydrogen from 3 water molecule. 3 oxygen plus 2 oxygen is 5 oxygen, plus 3 is 8 oxygen. This is the way to balance the equation with Al2O3 and NaOH. I did say earlier that there is actually another possible equations. I don't normally remember the equation, but you have written down something that makes sense and you check the marking scheme is fine, then I'm sure it's fine. All right, but this is the usual equation I normally think of, and that follows through from my Al3 plus qualitative analysis case study, and I get this colorless solution when it dissolve in excess NaOH there. Now part C, how does the presence of an impurity, so you need to name this impurity and you need to explain. So there are 2 bits to that thing here. This is carbonaceous, so this means carbon containing fuel. This is now in environmental chemistry. I know this for a fact. It is in the O-level 2023 syllabus onwards that specify exactly, even in the combined science syllabus, they said that sulfur dioxide can come from burning carbonaceous or carbon containing fuel that contain traces of sulfur impurity. So this is sulfur as a solid present as an impurity in carbon containing fuel. So combustion of the fuel, combustion of carbon containing fuel or carbonaceous fuel, basically hydrocarbons with sulfur pollutant or with sulfur impurities produce sulfur dioxide, produce SO2 gas. And what does this SO2 gas do? So the SO2 gas gets oxidized by NO2 gas in the upper atmosphere, forming acid rain, forming SO3 actually, forming SO3 gas that can then form acid rain. So they are not asking for equation here, but if I write equations instead of writing a lot of words, that should have been acceptable as well. So first of all, when you burn sulfur, you're going to get SO2, and that SO2 can escape to the upper atmosphere. And the key reaction is the SO2 react with NO2, and you're going to get NO plus SO3. This is not in equilibrium. You are not in industry. This is not man-made. This is nature in the upper atmosphere. The NO2 is actually a catalyst because the NO can regenerate back to NO2 by getting oxidized with the oxygen in the air. But my focus here is to show how does this burning this sulfur in the carbon containing fuels lead to acid rain. So I will skip that step there. This will give you H2SO4, which is your acid rain. It is, after all, chemistry exam. If you don't feel like writing a lot for your explanations, you can obviously, write some equations, and that will substitute all the words here as well. But you got to name the impurity as that is required in the question there. And that's the end of that 14 marks inorganic question. In this question number 4, we have the start of organic chemistry. We have halogenoalkanes. Halogenoalkanes, 2-bromobutane, so 4-carbon alkane. If I start drawing skeletal formula, because if you know my tutorials, you know that I'm a big fan and proponent of skeletal formulas. So, whatever you do, try to master skeletal formula. Carbon form 4 bond, you have 1 covalent bond there, so there is 3 hydrogen, CH3. Carbon form 4 bond, 1, 2, 3. So there is 1 hydrogen there. And the Br is a branch. Carbon form 4 bond, 1 and 2. So there is 2 more hydrogen there. And carbon form 4 bond, 1, 2, and 3 hydrogen there remaining, because you already show 1 bond forming to the carbon there. So this is a structural formula for these 2-bromobutane. The bromine is the branch at position 2 there. Now you react in 2 different ways with sodium hydroxide, halogenoalkane chemistry with sodium hydroxide, as you know from my topical tutorials, and those are all entirely free for anyone to view. So make sure you try and go through them. It's hydrolysis, which is essentially the substitution of the Cl or Br or iodine, the halogen, with a OH group, using sodium hydroxide in water. What was I talking about? Hydrolysis there, the hydro means in water. So that means aqueous conditions. So this is NaOH in aqueous conditions. For elimination, you need NaOH in ethanol. Both of them, you need reflux as well for your heat. Okay, so it's just the choice of your solvent, water, because you're doing hydrolysis of the halogenoalkane, or ethanol if you want to favor elimination there. So here, when you warm it with aqueous sodium hydroxide, you get an alcohol that can exist as a pair of optical isomers. So these are the enantiomers, the non-superimposable mirror images of each other. They want specifically the name of the mechanism as stated in the introductory organic chemistry. When they produce these alcohol, they are going to undergo a substitution type of reaction, but the mechanism is going to call nucleophilic substitution, as the OH minus act as a nucleophile. If you want, you can also, actually, you cannot tell whether it's SN1 or SN2, because this thing here is a secondary halogenoalkane. The carbon with the halogen is bonded to 1 and 2 other carbon. While it is easy to say primary halogenoalkane prefer SN1, secondary halogenoalkane is tricky to tell because it's intermediate, so it depends on experimental data, and you will find more of these kind of questions in A2 rate of reaction. Now explain why the alcohol produced exists as a pair of optical isomers. Well, if you replace these with hydroxide and you have to do this with aqueous NaOH, NaOH in water, and reflux, and you get the OH like that. I haven't balanced my equations, but if you have NaOH, then you kick out NaBr. The idea there really is the Br get replaced and substituted with the OH, and you get alcohol there. Now this carbon with the OH, 1 OH, 1 CH3, 1 CH2CH3, and 1 hydrogen. In skeletal formula, we don't show the hydrogen bonded to the carbon. Carbon form 4 bond, 1, 2, and 3. There is 1 hydrogen there. So basically they're asking you what is meant by optical isomer. That's the nature of this question. Okay, so it has a chiral carbon, and that is not enough. There are 2 lines. Its explanation is not state. So that means the carbon there is bonded to 4 different atoms or groups. It's not always just atoms. In this case, you have hydrogen atom, but you also have groups of atoms like the alkyl, like the OH, etc., etc. This kind of question always try to give you some free marks. 3-dimensional structure. We know that carbon form 4 bond, that is a carbon sp3, 4 bond pairs and 0 lone pairs. So the 4 bond pairs repel equally, and you get tetrahedral geometry. And tetrahedral geometry is 109.5 degree. You have to display it at the tetrahedral center there. So 2 flat line, and then 1 is coming out. This is bolded because it's pointing at you right in the eye, coming up from the screen. This is away from the screen, behind the screen there. And I have to draw the mirror image. So draw the mirror image first before putting anything in. So the wedge one, the bolded one, the bolded one is away from you, away from the mirror. Well, when I say away, what I mean is it pointing at you right in the eye, but it's pointing towards the left. So this is pointing towards the right, but it's still coming out from the screen towards you. And the 2 flat one, this and these are flat. So this and these are flat. They are mirror images of each other. Now, just because we have done the geometry correctly, we haven't put in the groups yet. So typically speaking, I would almost always put the longest group on top here, because it's easy to write horizontally like this: CH2, CH3, CH2, CH3. We do not have to write CH2, CH3 from right to left, because this is a single bond. You can rotate. You like to draw the mirror image like that? Sure, but you can rotate about the single bond, so there's no difference with writing it like this as well. You should get the connectivity correct. So the next one will be, let's say, the CH3. So things like CH3 will be like that. If you write CH3, that is okay, but your bond is really between carbon and carbon. You should really try to be correct as much as possible. So the bond is between carbon and carbon. The bond is between carbon and carbon. 3 hydrogen. You read it as CH3 like that. Okay. Now to the next one, you also have a hydrogen and an OH. So an OH and OH, and last but not least, a hydrogen. To be honest, does it matter where you put the groups around? It does not matter, as long as you have the projector to the correct position in the mirror image, and as long as you have the 4 different groups as you have seen from this skeletal formula of the product, having replaced the Br with the OH there, because you want the alcohol product there. And this is the chiral carbon bonded to 4 different groups or 4 different atoms there. Now this next bit is basically asking you, when you use ethanolic sodium hydroxide, basically this reaction is elimination. So give the name of the mechanism. You don't really do elimination mechanism in AS that much, at least not in the old syllabus, and also not really in the new syllabus, to be honest. But what you can say is, when you have 2 bromobutane, so I've drawn it slightly differently here, but again we have to put in the lowest number for the branch group there. So you have 2 different carbons here, because you gotta remove the hydrogen from the neighboring or from the adjacent carbon or the neighboring carbon. You cannot remove the hydrogen from the same carbon with the halogen, because you're trying to form the double bond. So this is a CH3 hydrogen. It's different from this adjacent carbon number 3 here, because that would be a CH2 hydrogen. The black color one is different from the green color one, because there's only 2 hydrogen here. There's 3 hydrogen there. 2 and 3 are not the same. This hydrogen black color one and this green color one will not be the same. If I remove from the black color hydrogens, my double bond will be 2 and 3, somewhere in between, and I can have cis and trans isomer. That is your trans isomer. That is your cis isomer, because they're on the same side, they're on the different side. You have geometric isomerism in the AS syllabus. But we have to consider the other product as well, which is coming from the elimination from this green color hydrogen. So what do I get? If I remove from the green color hydrogen, then my double bond is between 1 and 2, terminal there. So that is going to be called, well, there's 1, 2, 3, and 4. So that is your but1-ene. Whereas for the black color one, you will get but2-ene. So one of them is trans but2-ene, the other one is cis but2-ene. All together, considering stereoisomers, because geometric isomers are stereoisomers, and also structural isomer, for which there are no other structural isomer of these. There are 3 possible products altogether. Very common type of questions in multiple choice chemistry as well. And not too surprisingly, they're asking you to draw and name the structure of the pair of geometrical isomers. I literally just explained that. I mean, I roughly know how these kind of questions will proceed. And when you have done quite a few papers, if you have gone through my topical playlists, then you will be able to see what I'm talking about as well. You will see that here, they said draw and name the structures. They don't mention display, skeletal or structural. That means could be any form, but not molecular. You cannot write molecular formula. That doesn't show the structure. You cannot write structural formula. Structural formula cannot show the structure. Only displayed, yes, because you want to show cis and trans. Cis and trans geometric isomers, they are stereoisomer. Stereoisomers definitions, same molecular formula, same structural formula. You try to write differently, they will have the same structural formula. You cannot show the difference at all. So you can only do display, or you can do skeletal. Both of them are acceptable here to show cis and trans, and I already named it previously. They are trans butene because you want the lowest number, 1, 2, 3, 4, which is the same as 1, 2, 3, 4 trans because they are at opposite positions on that carbon there. On the other hand, that is your cis butene. So this one is your, these are your geometric isomers. So they have a carbon-carbon double bond. First condition. Second condition, they must not have the same group on the same carbon, must not have the same group or atoms on the same carbon of the carbon-carbon double bond. This is the hydrogen, this is a methyl, this is a hydrogen, this is a methyl. They are not the same, they are not the same. Obviously, you have cis and trans geometric isomers there. Now, you want the third alkene. I also did that. And they ask you why it doesn't show the cis and trans. So basically, in the previous question, I already explained what gives rise to cis and trans. So, we are trying to explain why this one doesn't give rise to cis and trans. If you draw this, you don't get the mark because they specify on name. But I draw it so that I could name it properly. So it's built one in. That's the first bit of the question. Second bit of the question, why this one does not show geometric isomerism. So on one end of the carbon double bond, even though you have carbon-carbon double bond, but on one end of the carbon-carbon double bond, I'm looking at this CH2 double bond. CH2 double bond, there are two same atoms, or in different cases, two same groups of atoms. Therefore, cannot have cis and trans. The requirement for geometric isomerism is not just carbon-carbon double bond. You must have different groups or different atoms, different groups or atoms on one carbon of the carbon-carbon double bond. So, you cannot have a CH2 on that side there. Even though there's that, you can move it around. You will never get cis and trans if you have two atoms or two groups that are the same on one carbon of the carbon-carbon double bond there. All right. Now to part B, we're given some reaction scheme here. The best thing to do with this kind of question is to draw and see for yourself. There's always the advice I give for students. So 2-bromopropane, and what we get here is we have done a substitution, and we have replaced the Br with NH2. This is what you call substitution. This is what you call type of reaction. Type of reaction is as stated in the AS Introductory Organic Chemistry syllabus. We don't know what X is, but we can suggest what X is from the next reaction. When you hydrolyze X, you are going to get this thing here, CH3, CH2, CO2H. So you get acid, you get carboxylic acid. That is strange. Don't know what that is. We'll think about it in a little bit. Can we? Oh, hang on. And also that thing there. So you get back this thing after you remove it. So you get an amine and you get a carboxylic acid. You get an amine and you get a carboxylic acid. So amine and carboxylic acid, if you work backward, is the opposite of hydrolysis. It's going to call condensation. Is also another type of reaction in AS Introductory Organic Chemistry. You will get something called amide. So if I think about my amine and my carboxylic acid, 3 carbon carboxylic acid, CH3, CH2, CO2H, and I get my amine H2N like that, and that comes from here. So I will lose the OH from the acid and I will lose the H from the amine. So this gives me X being the amide, which is like this, and then I have a new amide bond, which is actually this one. So N and then H and then like this. So this is the amide bond that I formed in reaction 2. So that must be condensation with this carboxylic acid, and then when I hydrolyze this amide, then I'll get back the 3 carbon carboxylic acid and these 2-aminopropane. This is called 2-aminopropane. So it's the amine group at position number 2. So 2-aminopropane there. So how about this next thing here? If I look at carboxylic acid, as they want you to think about the reaction 4 from this main reactant and not from the other products. So looking at the carboxylic acid, which is this propanoic acid, 3 carbon acid, giving you 3 carbon alcohol, 1, 2, and 3. That is propane, 1 all. And then that alcohol there give you something else, which is then substitution at position 2. So I had substitution at position 1. Now I move to substitution at position 2 after I reacted with HBr. So when I work backward, if this is addition, the type of reaction is addition, the opposite of addition, going the other way. So from top to bottom, that must be elimination. Elimination, just like we did earlier, is to remove one of these hydrogen. But this is totally symmetrical. So this is a CH3 and this is a CH3. So removing from this hydrogen is the same as removing from that hydrogen. I could get this. It is the same as this one, which is prop 1 in. And you can do addition reaction, and the mechanism will be electrophilic addition mechanism. And from alcohol to alkene, this of course is an elimination mechanism, elimination reaction as well. And then the mechanism will be elimination mechanism as well. So you don't really deal a lot with elimination mechanism in the Cambridge International A-Level, but you do deal with the elimination type of reaction there. We've already kind of reviewed the whole reaction scheme there, what is going to happen. So now state the reagent needed for reaction 1. You just need to hydrolyze. This again is hydrolysis. So you need to break the carbon-bromine polar bond, delta plus, delta minus. And you have to replace it with NH2. So it is not hydrolysis, I beg your pardon. Hydrolysis will produce alcohol, like in the previous question, using aqueous NaOH. But here, you want to get NH2. So what you need is, you need concentrated NH3 or con NH3, and this is in ethanol. The solvent is very important. You don't deal it in aqueous solution, you deal it in ethanol, so that you don't have the competition for hydrolysis or for any sort of substitution with the OH from the water at all. So con NH3 in ethanol, and usually you heat in a sealed tube, but they don't ask for the conditions. Otherwise, the condition will be heat in a sealed tube for high enough pressure. State the condition for reaction 2. This is a condensation reaction, and I knew the reactant when I work backward by by condensing these two products together between carboxylic acid and amine, and I got this amide where the carboxylic acid will have lost the OH and the amine lost the H, and I get the CONH amide chemistry there. So the reagent for reaction 2 has to be CH3, CH2, CO2H. It condensed together with these amine there to give you an amide. Give the structural formula. So here they specifically want the structural formula for X. What I did was I did the skeletal formula for X, so it will not be accepted, but we can very easily have drawn the skeletal formula, and then we read how many hydrogen is here. Carbon form 4 bonds, so it form 1 bond there, so there is a CH3. And then carbon form 4 bond, 1 and 2, so this is a CH2. Carbon form 4 bond, there is a 1, 2 for the oxygen, and then 3 and 4, so there is no oxygen. It is just CO and H. This is the amide, CO and H. And then now carbon form 4 bond, 1, 2, 3, so there's 1 hydrogen there, CH. If we consider this as the branch, then the branch will be CH3, and then on the main chain I have a CH3. So this is a CH. If this is the main chain, is CH3, but then the branch is CH3 there, I put in a bracket there. You could also read from right to left. If you read from right to left, if you go this way, you will have CH3, CH, and then CH3, because this is your main chain, let's say, then this is CH, and then your branch is CH3, and now I'm on the NH, so NH, and then CO, NH, and then CO, and then CH2, CH3. Skeletal formula is the same, whether you draw left or right, I guess, but you know, the positioning will be different. They want structural formula, so this black color one is correct, this blue color one will be correct as well, but skeletal formula, it is the correct product, but it will not be credited here because they specifically want the structural formula there. Now part 4, name the type of reaction in reaction 4 and suggest a suitable reagent. There are two types, there are two questions being asked here. Reaction 4 was converting the carboxylic acid into alcohol. To reduce the carboxylic acid into alcohol, you need a very strong reducing agent. Sodium borohydride will not be strong enough to reduce carboxylic acid. You definitely need a much stronger reducing agent, and to do that you need LiAlH4, lithium aluminum hydride. You do this in dry ether, as lithium aluminum hydride is very sensitive to water, and you do need to reflux it as well. Although they don't mention the condition, I usually just include the condition. If you forget it, this is the one that will get the marks, not the condition here. For reaction 5, this is the elimination of H2O from alcohol to give you alkene. You can do this with corn sulfuric acid as your reagent, but this particular question says what is a solid catalyst, so you can do it via a different method where you just heat it over Al2O3 or SiO2. Typically, we would just use Al2O3. It's just something that would speed up the release of this H2O, the elimination of H2O from alcohol to give you the alkene there. But hang on. I would not get the marks because they want the name. So I should really write down the name, aluminium oxide there. Okay. So they want a catalyst. If you put corn sulfuric acid there, concentrated sulfuric acid is actually a reactant that is used to kick off the H2O. So actually corn sulfuric acid will work as well. Yeah. Corn sulfuric acid could be the answer as well. So you could use concentrated sulfuric acid as well. But of course, that again is formula. They want the name, so that cannot be the answer. You have to give the name concentrated sulfuric acid. So both of them, this one you hit the alcohol, cover in a cotton wool over this particular solid, and you collect the alkene. This one, similar method I guess, because this will remove the water as a dehydrating agent there. Feel this question is a bit long. What do we want? We want to produce 2-bromopropane from Y in reaction 6. Reaction 6 was alkene, prop 1 int, adding HBr onto the halogen alkane, so it's the electrophilic addition mechanism. So what we are getting there is we are getting like this plus HBr, and then we get this 2-bromopropane there. So we need to complete this electrophilic addition mechanism for alkene. So you can draw structural, you can draw display, you can draw skeletal. So I think, let me just draw display so that it is clear, but you can draw skeletal, there's no problem whatsoever. When I say display, I mean this is going to be structural, partially display I guess, or partial structural. The first thing that will happen is dipole. Dipole, whether this is polar or not, but in this case it is polar, so the dipole there is delta plus on the hydrogen, delta minus on the more electronegative bromine. Rich in electrons from the alkene, not from the carbon, from the alkene, rich in electron, attack point electrons, then it breaks the Br hydrogen bond, and it will give the 2 electrons to the bromine, and now you will have an intermediate, which is carbocation. We could see that we could get potentially two carbocation. Where the hydrogen adds there, I'll get the plus there. But when the hydrogen adds here, I'll get the plus here. I want to get 2 bromopropane. So I want the plus to be there on the carbon number 2 because we are going to form that particular product later on. As the Br now is a negative charge, it has a lone pair, and this from the lone pair attack the carbon. The lone pair doesn't attack the positive charge, it attacks the carbon with the positive charge, rich in electron, attacks the poor in electrons, and now this is carbon 1, 2, 3 or 1, 2, 3. It is the carbon position number 2 with the positive charge that the lone pair attacks and give you this 2 bromopropane. Alright. Now give the name of the mechanism. I already talked about electrophilic addition earlier. So we know that this is electrophilic addition, the rich attacking the poor. The alkene is the nucleophile, this is the electrophile. You have done addition of the electrophile onto alkene, it's called electrophilic addition there. The very last bit of this whole 22 marks question is this 2 marks question asking you why 2 bromopropane is the major product of reaction 6, but 1 bromopropane is a minor product. This comes down to this mechanism where previously we only show 1 intermediate because this was the intermediate that will give you this product. So what I could comment on is this is secondary halogenal alkane. So 2 bromopropane. Better spell that properly. 2 bromopropane comes from this cation because the last step was the Br minus attack that bromine there. So the carbon with the positive charge, the carbon with the positive charge is bonded to 2 other carbons. There is 1 hydrogen there. So this is a secondary carbocation. Secondary, or usually what I write is 2 degree, that is the short form for secondary, and this is a carbocation intermediate. Now what I can say is 1 bromopropane. So 1 bromopropane, which I did not draw the intermediate earlier, but of course we can still produce it. It's just produced as a minor product. How do you know which intermediate it is? You break away, you try to break that bond there, and then you will get the positive charge on the end there because the Br minus with the lone pair will attack this bit here and complete the electrophilic addition mechanism just like it did when you form the 2 bromopropane. The Br minus lone pair attack this carbon in the center. When it is this thing here, the Br minus with the lone pair will attack this carbon end here. So what happened there? What happened there is this is a primary carbocation. How do I know it's primary carbocation? Because the carbon with the positive charge is bonded to 1 other carbon, primary carbocation. Overall, what can we say here? We can say that secondary carbocation is more stabilized compared to primary carbocation, and you have to explain. You cannot just state it's more stable. In fact, tertiary is more stable than secondary, more stable than primary carbocation, because we think about this thing called inductive effect. So there is an effect. If I just put this black color one, the arrow. So I don't like to draw this black color arrow because we are not doing mechanism, but it is showing that you are donating electrons. They are alkyl electron donating groups. So we can say when you are secondary, you have 2 times alkyl electron donating groups. When you are primary, you only have 1. When you are tertiary, your carbon with the positive charge is bonded to 3 other carbons. You will have 3 alkyl electron donating groups. That's why secondary carbocation more stable than secondary carbocation, more stable than primary carbocation. So we need to explain it because there are more alkyl electrons donating groups by inductive effect. Okay, this is as stated in the AS syllabus under alkene chemistry. So the more alkyl electron donating groups you have by inductive effect, you will stabilize the carbocation, which is poor in electron, stabilized by electron donating groups that can help to, help to stabilize these electron deficient, electron poor carbon there. Right? So that's it really. So on the major and minor product, and this is the origin of this Markovnikov rule. Not too sure if they still use this term in the syllabus, Markovnikov rule. But when they say Markovnikov rule, basically that means explain the stability of the carbocation in terms of this electron donating alkyl groups by inductive effect there. 2 marks questions. I have shown some diagram, that's why I'm using up the space. Otherwise, if I'm just using words, I might be able to just use the space within that 4 lines. The end of that 22 mark question there. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Follow me at ptet.chemistry on Facebook, Instagram, Twitter, and Telegram to get connected. And I'm not sure when the silver tier members only video will be available for everyone to watch, but thank you for supporting my channel. And if you haven't, so do consider upgrading to the silver tier membership for the price of a cup of coffee, and you can get access to all my yearly paper tutorials throughout the channel. And of course, the topical playlists are all for free, and they actually come from the yearly paper tutorial as well, but it's not the complete thing. Thank you for watching. I'll see you in the next tutorial video.